Good afternoon, London. Welcome to the AWS Summit, last session of the day, so it's really, really nice to see the room jam-packed like this. So I've got a very simple question for you guys. Put your hands up if you're using elastic load balancing. Right, for everyone who didn't put up your hands up, we need to have a chat. So what is elastic load balancing? So elastic load balancing automatically distributes incoming application traffic across multiple applications, microservices, and containers. And the applications, microservices, and containers that are hosted on the Amazon EC2 instances is really the important part that I want to talk about you guys today. So prior to August of last year, we were not capable of doing this segregation. We only had instances, and we only had single ports per instance. But with the advent of the application load balancer, which we'll focus on during this talk today, we are now able to support microservices and container-oriented architectures. And we'll talk about all of that in a bit. So what are the advantages of using elastic load balancer, right? Well, first of all, we're elastic. You don't need to run an LB on an EC2 instance. You don't need to worry about anything such as scaling. You just provision an elastic load balancer, whether it's a classic load balancer or an application load balancer, and we take care of the scaling. It's completely elastic, and it's completely transparent to you. As your application's traffic increases, as we see more things coming into the front end, we will scale that ability to process the traffic and send it through to your backend. And as you register more backend instances, we'll preemptively scale, because we know that you guys are smart, and if you are adding stuff on the backend, you might as well be doing something with it. It's secure, right? It would be of no use if this wasn't secure. We pay a lot of attention to everything that has to do with security on the load balancer. Our ELB engineering team had security as one of their main pillars. We have managed SSL, we have managed security policies, and with ALBs, you don't even need to worry about that. We manage everything for you on the background. We also integrate with a lot of AWS services, right? So if you were to deploy your own load balancer on your EC2 instances, how would you send metrics to CloudWatch? How would you auto-scale? You'd have to develop all of these integrations by hand, by yourself. Elastic load balancing integrates with 14 different AWS services, whether that's CloudWatch, whether that's auto-scaling. It's seamless, and you can use it right now. And we're cost-effective, right? You pay for the bandwidth, and you pay for the provisioning. But you don't have to guesstimate how much capacity you need, which means that you don't have to run costly, oversized EC2 instances with the software on them. We expand, and we're elastic on the front end, and we scale as the traffic comes in, which means that you only pay for what you use, and that is the provisioning of the ELB, and that is the bandwidth that the ELB uses. So when you and I and everyone else first started out in this business or in technology, this is probably what we did, right? You build an application, you probably put your database on the same application server, you spun up an Apache or ISS web server, and then you literally just pointed everyone to it. It's not something that I recommend. It has a lot of problems. There's a single point of failure, of course. It's exposed to the internet. And the idea here is that this wouldn't be an efficient solution for any business, right? We all know that. We all know that now. And as solution builders, we sometimes don't realize how good load balancers are and how much benefits they provide to us. If you think about things like garbage collection in Java, right? ELBs protect you against that. In this scenario, in this architecture, if you had a hiccup from that single EC2 instance, whether it's your database because it needs a bit more time to process that transaction, or because your JVM has stalled because it needs to go collect a bunch of garbage, you'd still be routing traffic there. So we do things like this. So we recommend that you use an elastic load balancer that routes your traffic to multiple instances on the background, right? And if you were to have one of those hiccups in this scenario, then the ELB would automatically route your traffic to a different instance. Now, we don't normally talk about the internal architecture and deployment of AWS services. But I feel that it's really, really important that we address one aspect of how elastic load balancers work. So ELBs, whether you choose to or not, use multiple availability zones. Even if you're in a single zone, even if your application, even if your solution is deployed in a single availability zone, we deploy ELBs across multiple availability zones. And the way that we handle routing traffic across multiple of those availability zones is with Route 53. So we use DNS to solve the availability and multi-zonal problem, and you get all of the benefit whether you choose to use it or not. This is super important because any time that you speak to an AWS employee, they will tell you you should be using multiple availability zones. We, as an ELB team, make use of all recommendations that we push out to our customers. And in effect, we are an AWS customer. We use AWS. We're a very, very, very demanding customer. We run the load balancers across multiple availability zones in a VPC. And we have the ability to load balance via Route 53 across those multiple zones and eventually forward the traffic to your VPC in a very secure fashion. So up until now, where you're using classic load balancings, you're using either of two cases, right? You're either using network or TCP load balancing, which is essentially layer 4 for the network savvy. And that supported TCP and SSL. It essentially bounds the incoming connections to a server connection. It is limited in that it cannot offer modification of headers. There's nothing that you can inject there. We just pass the packets as they come. We literally do not look at those packets other than saying there's an incoming packet, we've got a back-end bound connection, and we'll just forward that through. And you can use proxy protocol. So we do use proxy protocol to prepend the source IP, the origin of the connection, so that you can make use of that on the application. But essentially, we're not able to modify the headers, right? So you can't use an X-forwarded 4 or anything like that. On the other hand, we've got layer 7, or application load balancing, if you will. That focuses on HTTP, HTTPS, or SSL. And what happens here is a little bit different. So we terminate all of the connections on the load balancer. And we maintain a separate pool of connections to the backend instances that we will then reuse to send the traffic your way. We can modify the headers, and we do. So we put the client IP address in the X-forwarded 4 header that we attach to those packets. For a lot of years, mainly since 2009, ELB has supported both of this in a single product. And to be perfectly honest with you guys, layer 7 has always been okay, but we constantly hear about customers that they want better support, they want more features. So, Application Load Balancer, a completely new product that addresses what we've heard from you. The differences between classic, or formerly elastic load balancers, and what is now known as classic, and application load balancers is essentially the layer at which it operates, right? So classic load balancers, they still do layer 4, layer 7, but they concentrate mostly on TCP and SSL. With classic, we offer support for EC2 Classic. If you're still operating on EC2 Classic, come talk to me after this talk, and we'll help you migrate to VPC, which offers a lot of new features and a lot of improved features. We have health checks on both, even though the ones on Application Load Balancer have been significantly improved. We'll talk about those in a little bit. We've got enhanced cloud metrics. We've got a lot more information coming your way with the Application Load Balancer. And we've got 3 new features. So path-based routing, we'll take a look at that in a bit, but it's essentially the ability to route traffic depending on what path you're sending that to. That was complicated to do on ELB up until now, let's say. We've got container support. If you're using containers, whether it's Docker, Kubernetes, or whether you're using ECS, we've got support for sending traffic to the same instance on multiple ports. And we've done WebSockets and HTTP2 support. So Application Load Balancer is a feature-rich layer 7 load balancing solution. It is fully managed We manage everything, the infrastructure, the connection handling, the forwarding, the connection pools to the clients and to the backends, and the SSL security policies. It is highly available, it is scalable, it integrates with Autoscaling, and it's transparent to you, right? All of this is obviously transparent, the way that we always do things, the way that we like to do things. We like to take the heavy lifting away from you. It allows for multiple applications to be hosted behind a single load balancer. And this is an important one, right? This is an interesting and very important one. This is how your application would have normally looked on an elastic load balancer using a classic load balancer, right? You've got a couple of instances on the back end, they're registered to the ELB. So what happens if you want to host more than one domain? Or what happens if you want to host more than one application on that architecture or on that deployment? Well, what you normally do is you'd use DNS to solve this problem, right? You'd have your single domain, example.com, and then you have two subdomains. You have orders and images. Those would go to different ELBs, and then you'd have different sets of EC2 instances on the back end. This is cumbersome. This is honestly expensive, and to be perfectly fair, there has to be a better way of doing this. And there is. So with Application Load Balancer, a little bit counterintuitive that says ELB, but Elastic Load Balancing is the name of the service. With Application Load Balancers, you can now have predefined groups of instances, which we call target groups or targets. And what you can do is you can use a single domain, such as example.com, and then you can have multiple applications doing different things. So, for example, in this architecture, we've got our orders application, which is all of the traffic for which is routed to a group of instances. And we've got our images application. All of the content for that application is routed via the application load balancer to those instances. So you've got one DNS name, and you've got two paths, and based on a certain condition, we will route traffic to different sets of instances. This presents significant cost savings for our customers. The fact that you can host multiple applications on a single load balancer will decrease your hourly costs of provisioning load balancers. You will still have the bandwidth costs naturally, but you won't have to over-provision load balancers. Of course, we've heard from customers who've said, brilliant, I'm going to take my 250 plus applications that I've got a single ELB for, I'm just going to move everything to one ELB, right? That is brilliant. So consider the blast radius, consider isolation when you're designing with application load balancers. Yes, consolidating is good, but make sure that you do so with some form of criteria that allows for failure, right? Always design for failure, and that's what we want to say. It's still good to avoid single points of failure, even if they're managed ones and highly scalable ones. So application load balancers provide native support for microservices and container-based architectures. So this is huge. We've seen a huge transition in the recent years of moving from microservices, from big monolithic applications to microservices and container-based architectures. Previously, you had to provision multiple ELBs with one application on the front end for each one of them, and you had to provision single instances with single ports on the backends. And this limited your ability to make the most out of utilization for every EC2 instance, and to adopt a more elegant style of deploying and managing your infrastructure, if you will. With the application load balancer, you can register instances more than one time with the load balancer. So as long as you're giving us a different port every time, we'll allow you to register that instance as many times as you want. And of course, there's a limitation here of 65,000 because you only have a certain amount of usable ports minus operating system and other utilities. But the idea behind this is that if you want to reuse the same instance for multiple applications, or you want to use multiple containers within the same instance, you can now do that. If you're using Amazon ECS, which, by the way, guys, if you're not using it, you should go try it right now. But if you're using Amazon ECS, it will automatically register tasks against the load balancer. And the reason for this is simple, right? When you're spinning up tasks with ECS, we're giving you dynamic ports. There's no way for you to know what that's going to be before you spin it up. So why would we put the onus on you of writing a script that essentially reads the task description, finds out the port, and that's too complicated. We'll manage that for you in the background. And it can also be used with other container technologies, of course. So how do we fit containers in here, right? So we've got our application load balancer, we've got our target groups, we've got our EC2 instances in the back end. How do I make this a little bit microservices architected? Super simple. I just deploy my applications on ECS. This makes for even more cost optimizations. You're using a single load balancer for multiple applications, which are hosted on tasks or containers, making the most use or maximizing the utilization of every single EC2 instance. We think that these features will present an incredible amount of value for our customers. But I'm not going to tell you about it. I'm not going to tell you about the value that this delivers for our customers. I'm going to let Michaela and Tina from the CoOp talk to you about how they've been using application load balancers to maximize the value that they deliver to their customers. Please welcome them to the stage.
Hi, I'm Michaela Kirkevich, and I'm the Principal Service Manager at CoOp Digital. And I'm joined on stage by Tina Howell, and she's going to do the techie bit. So I'm just going to tell you a bit about CoOp's story. I think most of you will have probably seen a CoOp shop somewhere. We're everywhere from major cities to those tiny little Scottish islands with not much else on them. But we do a lot of other things as well. Most people don't know we've got a general insurance business, a legal services business, online electricals, and we're also the UK's biggest funeral care provider as well. And last year we stood up a new department in the CoOp, which is the digital team, which is where me and Tina work. And this was quite exciting because being a new area in the CoOp, we had this chance to bring in some new technologies and some new ways of working, and that's what we're going to talk a little bit about. So the thing that makes the CoOp different from most other supermarkets is that we are a CoOp, which means that we're owned by our members, and they have a say in the decisions that happen in our CoOp. The CoOp, when it was founded, was really pioneering. It was the first company that brought in the idea of a loyalty card. The more that you spend with a company, the more that you get back. But over the years, we got overtaken by the Tesco Club cards and the Nectar cards, and we sort of lost our way. So last year, we decided that we want to reinvigorate membership and make it mean something for our members. So we had a vision of a new proposition, which is as you buy more CoOp products and services, you get 5% cash back for you. But we're more than just that. You get 1% of what you spend goes back to a local cause that you choose in your community. We did some pretty amazing stuff. So we went from this vision to be able to launch a beta with our colleagues in just 12 months. And 3 months later, we launched to 8 million members. It was an amazing thing, but the thing that, for me, from a technical point of view, was even more amazing was on day one of launch, we realized that we weren't registering as many people as we thought we were. There was lots of people dropping out on the registration flow. And going from our pre-digital days in the old CoOp, where maybe if we're feeling brave, we might do quarterly releases on our services, we looked at what was happening on that registration flow, found the problem, made some changes, and turned it around in 24 hours, which was a really huge thing for us to do. For those of you doing continuous delivery, that probably feels like nothing, but going from those quarterly releases, it was quite a big success story for us. And at peak, we've been able to put 41 releases a week through our system, whilst keeping really good availability. Again, really big pluses for a company that's not used to working in that way at all. And when you do a project like this, when you do any project, there's always challenges. And I thought I'd just pick up a few that we thought were some interesting ones that ELBs have helped us with. So CoOp was traditionally in 2 physical data centers, which I think a lot of people that might be going on this journey, they might have businesses that are in physical data centers wanting to go into the cloud. There was one thing that made quite a big difference for us. So an example here is we wanted to make a port change. We share our data centers and our network and our load balancers with all those other business units that I talked about, and they've got different demands. So a retail customer has got different ideas of when their peak times are and what their risk appetite is to a general insurance company. And we've got all those different business units sharing some components. This means that if we want to make a network change, we've got to make sure that we're choosing the right time that doesn't impact those services. We have an internal team that coordinates that, and we've got to go through various change boards to be able to get that approved. So it took us 6 weeks to do a port change. And for a company for a team that's trying to do continuous delivery, that wasn't going to fly with us. And because our infrastructure was in that physical data center, it was a different team that was looking after it. So what we found was where we had a problem with a server, the first thing that we'd know about it is the server's fallen over and the service is impacted. And again, we didn't want that. We wanted to be able to act on that much more quickly. And then last of all, we wanted the service to be highly available. Everybody does. But we also wanted to make sure that we'd be able to make changes really quickly. We wanted to test and learn. We wanted that capability. But we also wanted it to be scalable. So we had an idea of what our members are like, what their usage patterns are like from our older version of the membership service. But what we didn't know was, as we relaunched it to our colleagues first and then our members, we didn't know what launch day would look like. We didn't know what the reaction would be after campaigns and how much people would use it. So we needed that ability to scale without buying lots of infrastructure up front. I'm going to pass over to Tina, and she's going to talk about how those decisions that we made in the design of our architecture helped us overcome some of these challenges.
Hello. We use elastic beanstalks. I've already done it, haven't I? We use elastic load balancers quite a lot in our setup, and I'm going to just reiterate some of the things that are key for that Michaela talked about. One is that we talked about the need for security, the need for the need for scalability, the ease of use for deployments, and what we did was we've actually templated our environments using Terraform. Now, if you look at the top part, when you make a web connection to a CoOp website, that's membership.coop.co.uk. That's all done through an encrypted method. When you hit the ELB is actually decrypts it and basically decrypts it and passes the traffic to the instance. Yeah, so what this allows us to do is, once it's passed the traffic to the instance, what we do is the health checks kick in. So if the instance is available, it allows the traffic to be passed. If it doesn't, basically the health checks actually fail the instance, and the auto-scaling group actually terminates the instance and provisions a new one. And the ELB actually brings it up. So that, for us as CoOp, is really big, because actually when we auto-scaled previously, we'd all have to do it manually using very manual methods of our servers. We also do blue-green deployments. So on the blue-green deployments, we bring up some new instances, and basically we can test the version before we actually bring it into the Elastic Load Balancer. And that's really great for us because we can test before we actually release. Previous to that, we used to do deploys on tops using Runnable. The other thing that's really good is we have finder.coop.co.uk. That means that we can basically auto-scale quite big. So at Easter and at Christmas, basically we get an average of from 2,000 connections to 15,000 connections. And that means we can auto-scale to quite a huge amount of servers in a small amount of time. And that's done all automatically for us, rather than doing the manual stuff that we do. So what's really good is that we've started to move to ALBs. Now, ALBs allow us to manage multi-products behind one URL. And that means the way that it's managed is just through different ports and different target groups. It also means that we've got better monitoring. So you can actually see where the resources have come from, and that's really important for us. All of that login goes into our Splunk and also into our Elk stack, and we do some Grafana login on it, and we also get our SecOps team to actually have a look at those logs. And if we see traffic coming from a different area, like Russia or, for example, China, we actually put blockage on our application firewall. The other thing that's good about the Elastic Load Balancer, so the Application Load Balancer, is that basically when we when we do health checks, we basically, when a node fails, basically what it'll do is it'll go to another instance automatically, and there's no problems. The user still continues as is. When it goes to when the auto-scaling group actually terminates the instance to bring up a new one, the application load balancer will bring it back. And for us, that's really important, because then the client sees, or the customer sees, that basically they don't have any issues on that connection. The really other good thing is most of our websites work under 200 response, so it's looking for that. It's saying actually that the 200 response is good. We do have some applications that run under 301 or 302, and basically what we have to do is we use the custom health checks that ALB allows us, and basically it looks for a different response code, and it's really great for that. What we're trying to do now is actually our tier 1 systems are being moved into multi-region, and we use latency-based DNS. Now we are working with AWS to do this more and more, so that all of our tier 1 systems are cross-region, never mind cross multi-AZs. I'm going to hand back to Michaela.
Okay, so this has given us lots of really great things. One thing I particularly like, so I run the on-call team. I'm also on the on-call rota, and I don't like getting those calls at 3 o'clock in the morning because the server's running a bit hot. So because we've got that automatic auto-scaling if something's looking a bit unhealthy, from a user's perspective, they don't even see it on the application. And from our perspective, we don't see it either. We just know that it will keep running. And that means that mine and Tina's teams, rather than being woken up in the middle of the night, we can focus on what was the root cause for that and how can we improve this service to make it even better. And that goes hand in hand with improving our availability of our services. So we've actually, since we've launched, we've been running really well. And most of the time where we've had issues, it's actually been user error rather than issues technologically. We've improved our security. So as Tina said, we've terraformed the templates for our ELBs. What this means is that when we have different product teams coming to us looking for a platform, we've already terraformed all the security policies that we want to include or exclude, and they're in those patterns, so we can just reuse them, and our security team loves this because it means that we've got some consistency in the way we're working. It might not fit the bill every time, and we might need to adapt it, but we know that 80% of it's there if we use those patterns where it's baked in from the beginning. And then it's enabled a faster rate of change. So we've been able to do exactly what Tina said. We've been able to do these deployments where we're health checking before we put things live. So that means I feel a little bit happier when product teams want to go really fast with their rate of change. What's next for us? So we're working even more with those patterns. What we want to do is when product teams are coming up with ideas, we don't want them to have to design their own platforms. We want to build those patterns so we can say, if you want one of these types of things, we've got a pattern for that. They use that, and that means that rather than them having to be trailblazers with the basics, they can come to us, use those patterns, and they've got a platform that they know is scalable and secure and performant, and they can focus on the things that really add the value to our end customers. I'm going to hand you back to Mariano.
Thank you very much, Tina. Thank you very much, Michaela. It's fantastic to hear about customer success cases and how they're leveraging new technologies to empower their customers. And that's it, guys. We're going to take a little bit of a trip through time and space. We're going to go really deep, and we're going to move really fast, and we're going to take a look at how the application load balancers work to empower customers like the co-op to meet their customers' needs, right? So we've got a really, really interesting API in the application load balancer. We've designed a completely new API from the ground up for this product. And what's the number one rule about designing APIs? Never, absolutely never break backwards compatibility. And that is exactly what we did. So our ELB engineering team spent a lot of time, and I'm talking months here, trying to make these new features work on the classic load balancer. And the reality is, it was just impossible, right? There was no way to get the benefits that we're after and be able to account for the trade-offs that we would have to. So what we did is we built a completely new product from the ground up. It's a new API. We broke backwards compatibility, and our customers are absolutely loving it. So this follows every single AWS best practice that we've ever laid for API design. We eat our own dog food, so we use load balancers, we use VPCs, we use our own products. We've learned a lot of lessons through the process of designing this new product and through the process of designing and maintaining the classic load balancer that we've poured into this product. And we've included a bunch of new resources, such as targets, target groups, and rules. And we're going to take a look at how those work to make your solution whole. So in the beginning, we had the load balancer. And the load balancer is essentially the main resource that you provision when you deploy an ALB. The load balancer needs to have listeners. So what is a listener? A listener is essentially an element or a resource that will capture incoming traffic into your application and allow the infrastructure behind the load balancer to forward that to your application. So it's the protocol and the ports that is defined within the listener. The listener, obviously, a little bit redundant, right? But the listener listens for incoming connections. And each load balancer will need at least one listener. You can have a maximum of 10. If you need more than 10 for whatever the reason is, talk to your technical account manager. If you don't have one, come talk to me after the session. And we define routing rules on those listeners to make sure that the traffic gets to where it needs to be. So what does that look like? We have our load balancer, we have our listeners, and now we've got target groups. We add target groups to the equation. And what the target group is essentially a target. And it sounds a little bit redundant. I apologize for that in advance. But the reality is that the listener will follow a certain set of conditions or rules to decide where it will forward your traffic to. So target groups are essentially logical groupings of stuff that sits behind the load balancer, stuff that will host your application. Generally speaking, a target, as we'll see later, is the association of an instance and a port. A target group can exist independently from the load balancer, right? If you go into your console, if you go into EC2, you will have target groups. They're independent from load balancers. You can have one without being associated to a load balancer. Generally speaking, the load balancer will need somewhere to route traffic to. And target groups are also a regional construct. And this is part of the reason that we decouple it from the load balancers. We want to make sure that it integrates with multiple AWS services. And one of those services is Autoscaling. Your target groups can, or the targets within the target groups can be auto-scaled by our auto-scaling services. And we'll take a look at that in a bit. So what's the next step here? Well, the next step is let's add some resources to those target groups, essentially some targets, so that we can route traffic to it from the load balancer. And a target used to be, in the days of the classic load balancer, just an instance and a port, right? A port that serves your application. And normally, that would be very fixed. You could only add the instance once. So with targets, with the advent of the application load balancer, we've got these resources, these targets, which are instances and ports together. And as I mentioned before, you can associate the same instance multiple times over, as long as you are giving us a different port all the time. You could even have a single instance sitting in a target group, and that be the only thing that you have behind your load balancer. That is perfectly valid as long as you give us multiple ports, and that would constitute multiple targets. A single target can be registered with multiple target groups, which means you don't have a one-to-one association. You can put the combination of instance and different ports along multiple targets. So a single instance can also help you host multiple instances of the same application. We then have rules. And the rules are the conditions that are going to help the load balancer determine where it needs to route traffic to. It provides the link between the listeners and the target groups, and it consists of conditions and actions. A condition is a rule, such as a path-based request / orders, and an action is what is taken after the condition is met. Today, we support forward. The idea is to expand that, obviously, but with the combination of the rule and the targets and the target groups, we can identify traffic that is going to a specific part of an application or to a specific application and make sure that it gets routed to the place that it needs to be. So what does a rule look like? Well, it's a path pattern. It is case sensitive. It can be up to 128 characters in length, and it can contain any of the following characters. Now, I would encourage you to read through this, but don't get too creative, right? You don't want a path that is too crazy. We also have API deletion protection for load balancers. We've had our Elastic Load Balancing team every now and then gets a request from a customer saying, hey guys, I accidentally deleted my load balancer. Would it be possible for you guys to recover it? And the answer is yes, most of the time, right? If the resources are there, if not too much time has elapsed, our engineers can actually go in and recover that load balancer. So much so that they built an internal API for it. We looked at the API and we said, well, we don't want to get calls at 3 o'clock in the morning for distressed customers. We should be resolving this problem before it even happens, right? This should never be a problem. So now you have your API deletion protection for application load balancers. Make sure to turn it on, and this will prevent your load balancers from accidentally getting deleted. Even if you don't have a need for path-based routing or multiple applications hosted on a single load balancer, it's still a good idea to use application load balancers. They provide a lot of performance enhancements for your application, even if that's just one application sitting on one instance. We have native support for WebSockets. Now, WebSockets is a new feature which allows for full duplex communication over a single TCP connection. This dramatically increases the speed at which your application is able to receive and process traffic. We also have support for HTTP2, which has improved page load times. And we have a lot of features beneath the hood that target media and entertainment workloads that essentially deal with real-time and streaming applications. We have a lot of customers in this space. We know that with classic load balancers, there's sometimes been challenges that translates to the user having to put up with buffering. Buffering is never good. You don't want any buffering during your binge watching of any new series. So with application load balancers, we've improved that dramatically. We've also driven improvements to application availability and scalability. The idea is your application needs to be available all of the time, and we need to make sure that we scale out. So if we look at this architecture again, right? So this is not highly available. This is not a very good design pattern, and it doesn't support a lot of the good stuff that we've designed lately. So I've mentioned health checks briefly before, and we've revisited our architecture. And health checks is part of the foundational stone of how the ALB is able to manage your applications or help deliver the traffic in an optimal fashion. So the health checks allow for traffic to be shifted on and off certain instances, right? If an instance becomes impaired, you don't want any traffic going there. If you have an application failure, if you have a hiccup, if you have timeouts in the application, you don't want any traffic being routed there. You want to move away from it. And that's exactly what we do, right? So as long as your instances are healthy, we will route instances across to all of them. And as soon as one of your instances, in this case the top one, becomes impaired or stops responding to health checks, we will move away from it. We'll stop routing traffic to it. Generally speaking, health checks do this very, very, very fast with minimal interruption or minimal impact to your application. Once the instance becomes healthy again, once the timeout elapses, or once we have the application responding in a timely fashion again, the load balancer can then start routing traffic back to that application, and you can be in full form. So we have multiple variations of health checks, so we have different types. We have HTTP and HTTPS health checks. You can customize the frequency, you can customize the failure threshold, and you can now, something that you can not necessarily do with a classical load balancer, you can get a list of successful response codes for either the timeouts or the failures of the health checks, right? Because one of the important things that you want to know when a health check fails is why is it failing? 99% of the time is a timeout, but you want to get an answer to why is this failing. And that's why we've also included detailed reasons for the health check failure, right? So these are available via the API. They're displayed in the management console, and they will tell you exactly why your application or why the load balancer has shifted away from a single instance. So we've also changed something else that we did, right? So failures. So what happened with classical load balancers if you removed every single instance from the load balancer? what would have happened is we would have returned the 503, right? And that would have left you wondering what exactly is going on. What we do here is if all instances behind the ALB are unhealthy, or they fail, or you just remove it, we're going to fail open, right? And cases where this is important is where you've got databases or a single master database behind a load balancer. A database can be taking additional time to handle a transaction, or you can have an application server that's doing garbage collection. The idea is that we are able to provide you the detailed reason why the health check is fine, and we're able to fail open, right? So a couple of things on health checks when you're designing them and when you're implementing them. We've seen a lot of customers implement health checks that either go too deep or are too broad. Best practices when implementing health checks for your application is remain shallow and remain simple. Make sure that each health check is doing something useful and purposeful, and that compounded failures, such as a longer time to process a transaction, don't end up taking instances away from your rotation. Always, always, absolutely always use multiple availability zones, right? And this is not just something that we say, this is something that we practice, as we showed you during the ELV VPC architecture details. But it goes a little bit beyond that, right? So even if we are using multiple availability zones, and even if we're telling you to use multiple availability zones, and even if you don't, we will still use a multi-zonal architecture to deliver your traffic. So if your application was sitting in a single zone, we would still be using, at the load balancer level, multiple zones that we route the traffic to. If you don't have any resources on a specific zone, we will still have load balancer resources there, and we will transfer the traffic cross-zone to you without any charges. So the charges that would normally apply for inter-availability zone data transfer are negated in this place. We've taken them away because this is not a responsibility that our customers should bear. It's also more cost-effective to use multiple zones. If you were to take an application that needs 6 instances to serve the peak amount of requests, and you were using a single zone, you'd have to have 6 instances in that zone, right? Any failure puts you below the number that you want to be at. If you're using 2 zones and you want to stay resilient and highly available, then that means that you would have to over-provision by about 100%. We should never lose 2 zones at the same time for the same reason. But in the event of a single zone loss, you would have to have accounted for 100% of the capacity in an alternate zone. Now, if you move to 3 zones, it reduces the amount of over-provision capacity that you need to have by 50%. Instead of having 12 instances split across 2 availability zones, you can have 3 instances in each one of 3 availability zones, and if any of those were to go down, you would still have 100% of the capacity that you need. That is 9 instances versus 12. The maths are super easy. It can bring some challenges, though, right? We understand that using multiple zones brings some challenges, and one of them is imbalanced instance capacity, right? So if you're using Route 53, if you're using URLs to forward your traffic as you normally would, what can happen is you can have caches that don't respect the TTL for the records and don't update the IP addresses. You could have clients who resolve once and then refuse to ever resolve again, because why would you check if the domain is still valid? So what we can see is that there are certain situations where you can have a lot more load on instances in one availability zone versus the other availability zones. And what we've proposed to solve this, or the feature that we offer for you guys to solve this, is cross-zone load balancing. So if you have resources across multiple zones, and you register those against the same load balancer, what we will do is we'll effectively load balance across the 2 zones that you've registered backend instances in. All zones get the same amount of traffic. The traffic is distributed evenly across the zones that you've got registered instances in. And furthermore, we also keep track of how many backend instances you have in each zone. So if you were to have 3 instances in one zone and 1 in another, we wouldn't be sending 50% of the traffic to each zone. We'd actually be sending an adequate amount of traffic for the amount of instances that you have. This absorbs the impact of DNS caching. It resolves the problem of imbalances on the backend. And again, as I mentioned before, we don't transfer those bandwidth charges for you. We resolve that problem for you. It's enabled by default on all application load balancers. And we will, so right now you can't really turn it off. The idea is that we will in the future be adding a feature for zonal architectures that use a single zone for whatever valid reason you have to do that. Autoscaling also supports target groups. So you can auto-scale your target groups independently and individually from each other. Because why not, right? So now you've moved into an architecture where you are hosting multiple applications off the same load balancer and you've got multiple target groups. Why would you scale everything out at the same time, right? Maybe your orders are doing more work than your images. Maybe your images are a little bit more popular than the sale of your product is. So the idea is that target groups can be scaled independently of each other. If your images are doing more work, then we add instances there. And when you've done doing that, sorry, I thought I had another, sorry, apologies. I thought I had a nice slide where it's scaled down. So when your images are being requested with a lot of frequency, we'll scale that up, the individual target group. And as the traffic becomes a little bit less and the request count dies a little bit down on the load balancer, we will scale that down. Bear in mind that even when you're using autoscaling, particularly when you're using autoscaling, you are always running at peak. And this is something very interesting because our customer said, well, but our peak is about 10,000 requests per minute. Surely when we're at 1,000, we're not running at peak capacity. It's like, well, no, but you've taken a bunch of instances away from the load balancer. So the processes on the instances or on the tasks or on the backend resources are still putting those resources under load. And security, right? So we've not touched too much on security today, but this is a fundamental pillar of ELB development and engineering. It's become complicated for customers. We understand it's very, very hard to become a security expert. So it's easier to become a marketer and give vulnerabilities new trendy names than it is to actually keep up with all of them and with what the resolution for each one of those is. So new ciphers are generally super secure, and of course that's because no browsers use them, right? So they haven't been broken yet. So how do you know if you need to apply a separate cipher? How do you need if you need to change your security policies? We've taken that all away with application load balancers. We managed absolutely everything for you. We understand that this is not easy, and we want to make it as easy and as simple as possible. We've also added SSL negotiation policies. These provide ciphers and protocols that adhere to the latest industry best practices. As I mentioned before, we manage those for you. And we've done two things. So first, we've integrated ACM, which is Amazon Certificate Manager. We'll talk about that in a second. And also, we test all of these things on Amazon.com. So Amazon.com has a huge amount of traffic. And what we'll do to understand if a cipher is secure or if a new managed security policy is what it needs to be is we'll run traffic from Amazon.com through our load balancers and figure that out, right? Do we need to keep support for RC4? Do we need to drop DES? ACM is an interesting one. It's not the subject of this talk, but I like to mention it. Amazon Certificate Manager gives you free certificates that you can directly integrate with your load balancer without having to email anyone anything at all, not a request, not a certificate, not a change certificate to sign anything with. And it doesn't require you to remember when you need to renew. I mean, I know for one that I've never had a problem with an expired certificate, right? So Amazon Certificate Manager handles the renewals for you as well. Application load balancers support security groups to limit access to your application, right? That's always been the case. And we've now integrated our web application firewall to the ALB product. AWS WAF monitors requests coming into the load balancer and protects web application from malicious activity at the load balancer level. This is even before anything hits your application, your instances, or your containers. It blocks, it allows, or it counts the web requests based on whatever rules and conditions you've defined. It helps you protect from things like SQL injection, cross-site scripting, bad actors' IPs, bad bots, and flood attacks. We also improve the monitoring, right? It's great that we improve the security, but we need to help you guys understand what's going on with your application. So we've integrated application load balancers with CloudWatch metrics. We provide metrics for every load balancer. We provide detailed insight into the health of the load balancer and into the health of the target group and the targets behind that. They're all provided at 1-minute granularity. As I mentioned before, we provide them at the target group level. We provide it at the application or load balancer level. You can configure CloudWatch alarms to take action or to notify you when anything happens, right? When you go over a certain amount of requests or when you go under a certain amount of healthy hosts. You can...
Afternoon sessions have now finished. Drinks are being served in the Partner Expo area.
Clearly we're not done. If anyone wants to run out for a beer, you're welcome, but I promise this is very interesting. So you can use all of these metrics with autoscaling, right? You can autoscale based on any dimensions that you want that you can see on CloudWatch. And I want to look at some of these, right? So we've got the healthy host count. This is the number of healthy instances or tasks or resources in each availability zone behind your load balancer. The most common cause of a host or resource being unhealthy, as I mentioned before, is a timeout. So be very careful with being too aggressive about the timeout. Make sure that you test the health checks, right? By making repeated requests to the resources and the load balancer, by eventually taking out an instance or two and seeing how the metrics vary when you do. Look at this at a zonal dimension, at a zonal level, but make sure that you also look at the load balancer and the application layer. We also have metrics for latency. It measures the time that it takes in seconds from the moment that the packet hits the load balancer until it receives a response. And when I say I receive a response, I mean the load balancer, right? So from the moment that the first packet hits the load balancer to when your application has processed the request and send a response to the load balancer. This is super easy to test. Just send requests to the backend instances and make sure that you look at this metric. There is a minimum time, there's an average time, and there's a maximum time within the stats, and they will give you a good idea of what your upper and lower bounds for latency are, and make sure that you can adjust those timeouts appropriately. Access logs, as always, available from the load balancer, will help you debug individual requests if there's any specific counts. Now, application load balancers don't use search queue lengths. What are those? With classic load balancers, if we couldn't serve a request because the backends were oversubscribed at that specific point in time, what we would do is we would take that request and we would put it in a queue, right? And whenever we got to that request, whenever the backend instances were ready to process them, we would take that request and we would send it. And the result would be a reply that you needed probably 10 minutes ago. So not particularly useful. So with application load balancers, we think that a much better approach is to reject that connection and to let the client retry. So most browsers today, most clients today have a retry feature. And what we will do is we'll reject that connection and we'll let the client initiate a fresh connection. And we also have target group metrics. So there's a number of them. I encourage you to explore them in the AWS dashboard or the console. And the idea is that you also get a good understanding of what's happening at the target group level, not just at the application level. And this allows you to closely monitor what's going on with the resources or the instances. We've also introduced CloudWatch percentiles. So the idea is that you understand what portion of your users are experiencing what or have what experience. So we give you visibility into the 90th, 95th, 99th, and 99.9th percentiles. And essentially what the 90th percentile means is that 90% of my users have at least this latency or much better. So at Amazon.com, we always focus on the 99.9. And the way that we do this is we start from the 90. We want 90% of our users to have at least this good of experience. And then we move from the 90 to the 95 to the 99 and 99.9. It allows for aggressive goal setting, aggressive performance targets, which ultimately result in your customers having the best experience possible. This is what the dashboard looks like. So can't really see it, but you've got the blue line is the 50th percentile, which is not the average, it's slightly different. And then you've got the green line, which is the P99 or 99% of your usage or your users having that experience or much better. As with the classic load balancer, we've got access logs for the application load balancer. These provide detailed information on every single request that is processed. That includes the client IP address, the latency, the request path, what response the server gave, what response the load balancer gave the client, and what ciphers or protocols are being used, as well as what user agents your customers are using. this is a very good way of making a decision on whether you're going to disable RC4 or DES for your clients. So you can look at the access logs and you can figure out who's using what and who's using it where. So with application load balancers, we've also introduced request tracing, right? And this is very tightly knit together with what AWS or Amazon X-Ray is doing. So every single application load balancer inserts a unique trace identifier in every single request using a custom header, the Amazon Trace ID. They are preserved through the lifetime of the request. And if the request goes through multiple load balancers, we will prepend or we will append the trace ID with the new one. Just make sure that you don't forward your packets through 500 load balancers. That's never a good idea. The trace identifiers are included in the access logs, so you can see exactly what request took what routes or suffered what behavior or was subject to what routing. So, going to let you guys go in about 30 seconds, but the question comes up, right? Why should I use an application load balancer? When should I use an application load balancer? Should I be using the classic load balancer? This is far too complicated for me to make a decision. So remember the use cases, right? So the classic is more targeted towards TCP and SSL. It also supports layer 7, but the application load balancer is a lot better at that. If you're using classic, you will be using classic load balancers. So if you're using EC2 Classic, you will be using classic load balancers. Again, if you're still on EC2 Classic, come talk to me after the session, please. Application load balancers are great for EC2 VPC workloads. They have improved health checks, they have improved metrics on CloudWatch, and they also support the 3 new features, which is path-based routing, containers and microservices architectures, and WebSockets and HTTP2. So to sum up everything that we're talking about before, if you're using TCP, SSL, or you're still on EC2 Classic, use classic load balancers. For anything else that you're doing, even if you don't need path-based routing, use application load balancers. Please remember to complete your evaluations. Thank you for staying for 10 minutes beyond the time of the talk. And thank you for helping us develop these new features, because all of this comes from what you, our customers, tell us that you need.